Cool. Thank you for the invitation to speak. Um, yeah, so my talk is going to be about a different approach to Hasso-Key's L4 norm bound, which is originally joint work with Anshul Adve and building on work of Paul Nelson. I'll explain sort of what that means throughout the talk. Anyway, so a quick outline. We'll talk about the setup, some previous work, then we'll introduce the theorem, then we'll think a little bit about a classic theorem of Zygmund, and we'll sort of go into the details of the proof. Okay, so the setup. Okay, so let x be the quotient of the upper half plane by SL2Z, the modular surface, and then delta is like the hyperbolic Laplacian. I mean, I'm just defining things so that we're all talking about the same thing. So a Heca-Maus cusp form is an L2 normalized joint eigenfunction of both the Laplacian and these Heca operators, which are more number theoretically defined, but this is all like analytically defined. And we're going to take them to be L2 normalized. And so importantly, the spectrum of these joint eigenfunctions is discrete. So we can index the forms with natural numbers, and I'll often index the eigenvalues also by these natural numbers. So the lambda j's are the Laplace eigenvalues, and then the tj's are the spectral parameters. But sometimes I'll refer to these things interchangeably. So one word of caution, at least if you're like new to looking at these things, is that the lambda sub j and the lambda of n are not the same thing. Yeah, but hopefully they won't get confused throughout the talk. Okay, so one sort of central problem is like this idea of equidistribution of mass. And so this surface is non-compact. It has finite volume with this measure. I put the 3 over pi there to normalize it, so that's a probability measure. Then I can state this theorem due to Lindenstrauss and Soundararajan that if you take a Heck eigenbasis of cusp forms with these eigenvalues, then in the limit, these squared values approach a volume. So what I'm really trying to say is like, you could take the square of a Maus form and defines like a measure on the surface. And this statement is basically saying in the high energy limit, these measures approach like the uniform measure. For every set that's nice enough. So there's some other conjectures about how mass might be equidistributed. And some people might put these under like Berry's random wave model, which is the idea that these Laplace eigenfunctions should behave like Gaussian random waves, at least in the high energy limit. All right, and whenever I say high energy limit, I just mean like as the spectral parameter goes to infinity, or like the high frequency limit. You can also think of the lambda j's as like the frequency of oscillation. And so one conjecture is the force moment conjecture, which is that, well, the force moment is exactly 3. And this comes from sort of the Gaussian model. And then a conjecture of Ivanich-Sarnak is that the L4 norm is bounded by the spectral parameter to the epsilon, which is kind of almost the best you can hope for. So I think both of these are known to hold under generalized Lindelof hypothesis. the first is a theorem of with Kane and Kahn, and the second, I don't know if I need to attribute it to anyone, but yeah. This talk will be about Key's proof of the second conjecture. The first is still unknown unconditionally. Okay, so the previous work on this problem, so most previous work I know of uses like the spectral approach, which is the approach that I would have tried if I was working on this problem. And so the idea is by Parseval, you could take the L4 norm and expand it into a basis. So these psi's are functions you've seen before. They're other Moss forms. The spectrum, the part of the spectrum I didn't tell you about is the continuous spectrum, which is full of Eisenstein series. And so if you sort of expand this out, this is the kind of expansion you get. And then the key insight is that by Watson-Achino triple product formulas, this square and this square are both related to L functions. And so typically trying to bound this fourth moment would kind of follow from getting strong bounds on these L functions, or at least these parameters, which are related to L functions. Okay. So just to be a bit more specific, in this case, you could write the square for this one as a local factor times some L functions. And so psi has spectral parameter T psi, and then phi j has spectral parameter Tj. And this looks it looks like there's a lot going on in this slide, but it's actually not so bad. So I want to concentrate on this local factor here. You can see that it has polynomial decay if psi oscillates slower than phi j squared. And that's just captured by this condition. In that case, the Tj term will dominate. It has constructive interference. If these guys sort of are about the same size, then this factor becomes much bigger than you might want it to be. And then if psi oscillates much faster than phi j squared, this term kicks in, giving it exponential decay. Otherwise, it's zero. And so like so this theorem that I wrote at the bottom due to Humphreys and Kahn, 2023, is that unconditionally they get this really strong bound on the L4 norm in terms of the spectral parameter. And the point is their method is through this spectral identity. They so they write down a spectral identity like this, turn it into a moment of L functions, and then carefully analyze the L functions and the local factors that arise in each of these ranges. But also an important extra ingredient is that they use sort of spectral reciprocity formulas to relate their moment of L functions to a different moment of L functions. And this is pretty important to their method. It's what allows them to get so close. So that was the best known. I don't know what the previous bound was before this one, but this one was a pretty good one. Okay, and then so around the same time of this paper, or at least the most recent version of this paper, Hasso Key proved unconditionally that for every epsilon greater than 0, the L4 norm is bounded by tj to the epsilon. So this is like an extremely important point, which in hindsight should be in the theorem statement. But Key's theorem is for the modular surface that I introduced in the beginning of the talk. But the theorem of Humphreys and Kahn holds for other arithmetic surfaces, including compact arithmetic surfaces. And so the reason why that's important is because Key's method is going to use the Fourier expansion of Cuss forms, and we don't have that Fourier expansion in the compact case. So this is still the best bound in those cases. But Sarnak's conjecture, or Ivanovich-Sarnak's conjecture, was, I think, originally just for the modular surface. So in this case, this resolves that conjecture. So the primary goal for the talk is to give a different proof of Key's result. And notably, we want to avoid carefully analyzing Bessel function asymptotics, which is kind of central in his work. And we want to introduce something more geometric. On the other hand, I don't want to give the impression that our proof is wildly different. Like, it's still going to be through the same methods of doing a Fourier expansion, analyzing the resulting ranges. But the key estimates are conceptually a little simpler, I think. But yeah, our approach, nor Key's approach, is via the spectral side. Okay. So, right. I'll say a little background about maybe how this idea to do things differently came together. So I think in 2023, Key's paper came out, and Anshul and I were grad students at Princeton at the time. And of course, Sarnak was very excited by this, so he sends us the paper to read. Around the same time, Paul Nelson wrote like an expository note kind of explaining Key's proof, but also simplifying it in a lot of ways. And one of the remarks from there's a remark in Nelson's like write-up that got Anshul and I thinking about how we might try to prove things a different way. And I'll say what that remark was later. But basically, both of us were coming into this from the perspective of microlocal analysis. I think for him, that perspective was, for Anshul, that perspective was maybe more in classical microlocal analysis side, and my perspective was sort of in the Nelson Venkatesh microlocal analysis side. But that was how we kind of thought about this. So as a warm up, and I think Sarnak for sort of alerting me to this theorem or bringing it to my attention. There's this old theorem of Zygmunt on bounds for Laplace eigenfunctions on the torus. And in some sense, this is not the best model for our problem, because these are sort of the eigenfunctions in this setting are very rigid because they're exact eigenfunctions. But anyway, the point is to just, Zygmunt's question asks, like, can you bound the LP norm by the L2 norm by a constant, let's say? And so on the case of the two torus, the L4 norm is bounded. So that's his theorem. It's kind of the like Laplace eigenfunctions on the torus analog of what we want to happen for Moss forms. So, okay, what does Zygmunt do? This proof is pretty easy, I guess. And this proof was I actually couldn't find Zygmunt's paper. So this proof was communicated to me by Sasha Loganov. So I thank him for showing me this. But anyway, the point is you can write the eigenfunction as like uh, an exponential sum. I should have wrote that this notation means like e to the 2 pi I argument. This is like e to the 2 pi I kx. And so because these are Laplace eigenfunctions, you know that the frequency has size like square root lambda. So that's where this condition comes in. And then we're going to impose a condition that the L2 norm is bounded. So note that this is the L2 norm of U, but it's also just the little L2 of the Fourier coefficients. And so saying the L2 norm is normalized is like having control over the Fourier coefficients. So then you just expand the square and you get a sum of different Fourier coefficients that have to add up to this L. But the point is that these indices also have to lie on circles of radius square root n, which is, you just think of n as square root lambda. I have to do this annoying normalization because I wrote 2 pi instead of just leaving it blank. But the point is, like, how many solutions could you have, right? You have one Fourier support is constrained on one circle, and then you have the other one which has to add up, like those two have to add up to L, and so that's like another circle centered at, so here I wrote it like, here's one circle, then the circle for M is constrained by that it has to be, M is the same as L minus K. So that's like another circle of radius n centered there. They can intersect in the most two places. As long as L is non-zero, I should say. Yeah. So this is kind of like, already we have like a geometric picture of what's happening. So then you can, by this geometric observation and Cauchy-Schwarz, you can bound the non-zero L's by the L2 norms of each set of coefficients. And in the zero case, you sort of have one diagonal contribution that's going to contribute. And if you put this all together, the 4 norm is the little L2 of the BLs, which we know is bounded each by the little L2 of the Fourier coefficients. And so the right-hand side is the 4th power of the L2 norm. And so as long as this is actually, yeah. So the point is that this finishes the proof, and the constant you get is like 5. Okay. So some remarks. So we needed a Fourier expansion and control on the Fourier coefficients. And we need an incidence estimate, which is kind of produced from orthogonality. And both of these things will come up again in the proof. Yeah, really, you could think of this actually as 3 things. Like, you need control on Fourier coefficients, you need some kind of orthogonality, and then that orthogonality will produce an incidence estimate that you can then solve. In this case, the incidence estimate is easy. In our case, it'll also be kind of easy, but yeah, we'll see. Okay, so let's talk about the proof. So we have to start with the Fourier-Whittaker expansion of these Moss forms. So if you take some point in the upper half plane, x plus iy, then you can expand the Moss form in this Fourier-Whittaker expansion in terms of the lambda of, and so these are the Hecke eigenvalues. This is the Whittaker function, and this is the regular e to the 2 pi I n x. So the first difference here, I mean, if you think about this, the difference between this and Laplace eigenfunctions on the two torus, we on the two torus, this would be like a e of ny. Instead, it's some other different function that we don't know much about yet. And then we have some Fourier coefficients, and they're kind of weighted by this square root of n. But kind of they're similar in sort of structure. So this Wt is the Whittaker function, and it can be described in terms of the Bessel function kit, like in this way. So yeah, this k is a well-known Bessel function, and its asymptotics are probably well studied, going back half a century at least. Well, way more than that, but yeah. So we have our Fourier expansion, and then the first thing we need is like control in the Fourier coefficients. And so in Key's proof, and in ours, because it's based on Key's proof, the only number theoretic input you need is like this fourth power bound on the Hecke eigenvalues. And this is called Ramanujan on average, because the Ramanujan conjecture says that the Hecke eigenvalues should basically be bounded. And so you have an average result for their fourth moment. I think this is due to Rankine, or maybe Rankine-Selberg. Yeah, this is kind of misleading. The proof here is not the proof of this theorem, but the proof of the Key's theorem, the L4 theorem. But anyway, so the L4 theorem will be proved by expanding. You'll just expand the fourth moment and use the Fourier expansion. And because the mostly unknown thing in the Fourier expansion is this Whittaker function, to do so, you'll need like a really strong understanding of Whittaker functions. And that's kind of what maybe this talk is about, like understanding Whittaker functions. Okay, so the behavior of Whittaker functions depends on the relative position of t, which is like the spectral parameter of your Moss form, and y, which is just the argument of the function. So here are the main regimes. The bulk range is kind of most of it, or at least most of the mass of it. Here it's going to be oscillatory, and this will be in the range where y is less than t, and it's like not too close to t, and too close meaning like within t to 1/3 of t. In the tail range, you have exponential decay. This is sort of the easiest to deal with. High in the cusp, the Moss form decays really quickly. And then we have this transition range, where close to t, within a t to 1/3 window of t, the Whittaker function gets a huge boost from the Airy function because of a type of singularity. And so this transition at y around t is sort of this classical turning point of the Bessel function. Yeah, so a quick note on notation. Unfortunately, my notation throughout the talk is not standardized. But y asymph to t just means that y is less than t, and also greater than t. So it's a round size t. Okay, so these are so these are the Whittaker function asymptotics. I pulled this from a paper of Ghosh, Reznikov, and Sarnak, which is probably overkill, but it's always where I look for these asymptotics because their normalization agrees with mine, and so it's convenient. And as you can see, like these are the different ranges of the Whittaker functions, and you have these asymptotics in terms of this H function, which looks kind of complicated. It actually isn't that complicated, but it looks kind of complicated. And so, you know, rolling up your sleeves and expanding the fourth power of these functions kind of looks daunting, at least. And then here's a picture of a Whittaker function. So you see, like it's very rapidly oscillating, and then where the argument is equal to the parameter, which in this case is like y around 15, it gets a huge boost from the area function. The boost does not last that long, and then you're instantly like decaying exponentially. Okay, so let's discuss the proof. So this setup is from Nelson's expository note. He starts by defining this n of w, which is like the fourth power of a semi-norm, um, for any function w. And sort of the key reduction is that the L4 norm bound is equivalent to showing this n of w, where w is the Whittaker function, is less than t to epsilon. And this works out because we should note the Whittaker function is also L2 normalized with respect to this measure. Okay, so this is what I mean when I say we're just going to expand the fourth power. It's going to look something like this. So there's a lot going on in this slide, but it's actually pretty simple. So you're going to get rid of the x integration by Parseval. So this will force an exact orthogonality, and you'll get a sum over n1 plus n2 equals n3 plus n4. You'll have all your Hecke eigenvalues, all your integers, and then you're left with this integral of Whittaker functions. And so you can see that the key thing to control is this integral because we kind of know exactly what these are. So in particular, putting absolute values in AMGM, you can turn this into a fourth moment, which looks good because we have a bound for the fourth moment, but not a bound for the individual terms. And then by symmetry, the contribution from each of these is 4 times the contribution of just one of them. So you can write this in terms of n1. And then so you have that n of w is bounded by this sort of fourth moment times this oscillatory integral. Okay. Okay, so this is just repeating what that is. But crucially, like in the tail and transition ranges, so 2 to 3 ranges, you don't need to use cancellation in the integral at all. You could get by with just this crude bound, which Paul proves in his expository note, that sort of this n of w, so if w, so we don't have to talk about Whittaker functions, but for any w, because this is defined for any w, if you know its support, if you know it's supported on some interval where these are roughly the same size and the gap is much bigger than 1, then you can bound this by the L infinity norm of the Whittaker function times the size of its support cubed over like the starting point of the interval squared. And super quickly, this comes from like, if you consider the support, like if W support in some interval, then that puts a constraint on each of n1y, n2y, n3y, n4y, which in turn puts a constraint on the n1, n2, n3, n4. And so you use the Ramanujan on average to count how many solutions you have with those n1s and those intervals. And then you'll be left with an integral over the support, which will of dy over y squared, which will contribute sort of this factor you see here, at least some of this factor. So that's where that comes from. And this crude bound is actually very useful. So we'll see why it's so useful. Okay, so there's 4 ranges. I've been saying there's 3 ranges, but it's kind of useful here to split it up a bit further, where you have y less than t and it's far from the transition range, and you have y less than t and it's sort of getting closer. So in these ranges, you have bounds for the Whittaker function. And these bounds follow from that screenshot of Bessel function asymptotics a few slides ago. And here we use that h function. Okay, and the only thing really we need to know about is that for this term, this factor in the exponential decay, this part will be positive, so it will decay exponentially. Okay, so what happens if we just plug these in? So if you sort of keep track of where y is, and then how far y is from t, and apply this crude bound lemma, in each of these ranges, you can write down the bound for w, and you can write down what you get if you plug in like y2 minus y1 cubed over y1 squared. And so, for example, in this bulk range, the resulting bound is y cubed over t squared. But recall that we want to prove it's less than t to the epsilon. And so this is only okay as long as y is less than t to 2/3 plus epsilon. And so this notation, this like curly less than, means like up to t to the epsilon. Okay, so we see that in the transition range and the decay range, just based on this like bound, we're fine because these are both smaller than t to the epsilon. And then in the bulk range, we're okay as long as some other conditions are met. And so basically the point is the only ranges that survive lie in the bulk range. And this is exactly where the Whittaker function is oscillatory. And so we're going to use that oscillation. Okay. So all the work in the bulk range is work of Anshul and I. So the point is, for simplicity of the talk, but it's also actually not, it's not that far from what's done in the paper, is that you can fix y in some compact interval like this, and n will be in this range, and this sort of characterizes the relevant bulk range. And so we write phi bulk of x plus iy to basically be the cutoff of phi in this range. And then we're going to change things. It'll be like convenient for us to sort of normalize the Whittaker function so that in this range it's kind of bounded by 1. And so what this has the effect of doing is when you rewrite it, you get rid of these square root n's and you have something that looks nicer, and then you get like a t to the minus 1/2 that you absorb. Okay. So Wn of y is still like quantitatively just like the Whittaker function, but it's just been normalized a bit. Okay, so the point is that this sort of term is a Laplace eigenfunction. The whole thing is a Laplace eigenfunction, so term by term, it's a Laplace eigenfunction. And so it solves a second order ODE. And this is the ODE you get. This is exactly the ODE you get. And so kind of one motivation to think of this is that because it solved this ODE, W and Y should oscillate at frequency like square root lambda. And so you might as well write it as the exponential of some function of size t. And so you take phi to be a complex supported smooth function, and you basically plug in what you would get if you took these derivatives. Okay. Now I'm ignoring some cross terms, but the point is actually that if you take phi to satisfy this equation, then the Whittaker function basically behaves like the exponential of t phi. Okay, I wish I had written this down on this slide, but you'll see it in like one more slide. But the point is, you can see from this equation that the points n and t phi prime lie on the upper half of the circle of radius square root lambda over t 2 pi y. So this is the key like observation, that the Whittaker function might oscillate at with some weird function that's maybe like some complicated arc cosine of blah blah, but importantly it lies on a circle. Those frequencies lie on a circle, or at least the derivative of that h function is something that lies on a circle, and so we can use that geometry. And so we want to show that W, in this case W of t, is actually Fourier supported on those frequencies. And so this is our proposition. So you can find standard smooth functions, which just means that the derivatives are all bounded, such that the Whittaker function is just a sum of these two phases. And the phases are given by this equation. Okay, so this is what I mean by like, oh, if the Whittaker function oscillates at frequency t, just write it as the exponential of t by some phase, and then that phase has to satisfy something like what the Laplace equation would suggest. So notably, you could read the oscillation just off the differential equation alone, and you don't need to sort of know anything about Bessel functions. Okay, so this is kind of mostly repeating myself, but the point is now we have that the ends and the sort of like second variable of frequency are points that lie on a circle. This is like the same as Zygmund's circle, except now the radius depends on y, but this is kind of okay because y is in a compact set, which is basically size 1. So now we can write our function by just expanding the Whittaker function into these chi n plus minus with the phases. And then when we expand the fourth power, we'll have these sort of 4 points on the circle. Okay. So the point is that we just pick like the plus, for example, the minus is similar. We get the same kind of equation. Now we have a t to the minus 2 in front because of our normalization. This n1 plus n2 equals n3 plus n4, that's the orthogonality. That's also saying that like the x midpoints of like if you draw two chords on the circle from these 4 points, the x midpoints are the same. Okay, and I've sort of combined our phase into one function here. And so the first thing to note is that the diagonal contribution which is just when n1, n2 are the same as n3, n4, then our phase is 0. And so we get exactly that this is bounded by t to epsilon using the Ramanujan bound on average. Okay, and so the bound is sort of saturated by this diagonal contribution. And the point is to show that the off-diagonal contribution is sort of also small. In reality, what we'll show is that most solutions are actually close to the diagonal solution and that you can't be very off-diagonal. And so how do we quantify this? So we can ignore this for now. It's just rephrasing what we need to do. But the point is, by stationary phase, this is basically an indicator of when the phase does not fluctuate by much. When the fluctuation is like smaller than 1, then that's where you can expect your contribution. And the more the phase oscillates, the more cancellation there will be, and this will be very small, and we won't need to worry about it. Okay, so the stationary condition is now forcing the midpoints in the y coordinate on our circle to be close together. So you have two chords, maybe on top of the circle, and they can't drift apart too far. Well, they can, but the further they drift apart in y distance, the more oscillation this will have and the smaller contribution it will be. And so this is sort of how we make that quantitative. So we show that this oscillatory integral, we give an upper bound based on the lower bound of the derivative. So if your derivative is at least m, then your oscillatory integral is less than 1 over m plus 1. That's basically all this is saying. So then you just need to prove this bound. And you need to show this is at most t squared because we have that t to the minus 2 normalization. And then this is just highlighting that like your derivative is exactly the difference in y coordinates. Okay. Okay. So now we need an incidence estimate because we want to count how many points you can have on the circle such that the x midpoints are the same and the y midpoints are close together. But instead of just considering the case where we're close together, we're just going to do it in terms of the derivative itself. So eta 1 plus eta 2 minus eta 3 minus eta 4 is the derivative of the phase. And so here's a sort of picture. If you let delta max be the maximum distance between the 4 points in the x coordinate, and then delta left right is the distance between the two closest ones, which by this orthogonality condition is the same if you take the right one or the left one, so it doesn't matter. Then basically we show that this distance is at least the inverse of the radius of the circle times the product of these two distances. And so this gives a bound for the derivative, a lower bound for the derivative, which is the m we wanted. Okay. And so, yeah, just to remark on this picture, like this is the sort of distance between the y midpoints, and that's controlling our derivative. And so the point is, if you try to stray very far away, the y distance would get bigger. That means more oscillation, so more cancellation, so smaller contribution. But the closer the y distance is, the closer these points are to being the same pairs of points. And that's why it's sort of approximating the diagonal contribution. Okay, so because delta max and delta left right are in terms of x coordinates, like the x distances, that means we can also write them in terms of n1, n2, n3, and n4, which is great. So if we just plug in the previous proposition, we get that mn is at most t inverse times delta max, delta left right. And these are at least n1 minus n3 times n1 minus n4. And by the orthogonality condition, we also could have written it as n2 and n4, n2 and n3, but it doesn't matter. It's the same. And so then we get an upper bound on its reciprocal. And this is just repeating what I said previously, is that if you try to have spread out points, the large vertical distance means the oscillatory integral is too small. And then here you have small oscillation, but there's not that many solutions to this. Okay, so after inserting the incidence bound, this is what you're left with. The forenorm is t to the minus 2 times your fourth power of Hecke eigenvalues, and then we have this incidence lower bound, which is our lower bound on the derivative of the phase. So you fix n1, because that's where your Hecke eigenvalues are. You pull that to the side. And then sum over n3, n4, and then n2 will be determined. So again, this is like generically the sum has t cubed terms. I think, so from here to here in this step, this t to inverse got absorbed in this t to minus 2, so now we only have a t to inverse. And the point is this sum, you can approximate it by integral, it's going to grow like a log of t. Or maybe a log squared of t. And so then applying our arithmetic input, the Ramanujan bound on average, we get that this is bounded by t inverse times t, which is 1. And again, this notation means up to t to epsilon. And that t to epsilon is coming from here. Okay. Are there any questions about this? It's fine if there aren't, because I have more material, which is kind of, they're just remarks and things, but I would say this completes sort of our geometric viewpoint of the proof, and then I'll say a little bit more about where that geometry, or where I think that geometry comes from, if there's no questions. So I'll just keep going, and then, obviously you can interrupt or whatever. Okay, but that was basically like our contribution to the story, is that like these Bessel function asymptotics, you don't have to do them. You can write down the ODE, see that the points lie on the circle, see that those points are exactly the derivative of the phase, stationary phase, and orthogonality impose conditions on the arrangement of those points in the circle, and then you count how many points there are. Oh yeah, so I have the summary of the proof. It's convenient. I'm gonna skip it for time because I just kind of summarized it. Okay, so here's some remarks. That's like, so how do you think about this circle, right? So the circle kind of comes up a couple times. We saw sort of an ODE incarnation given by this iconal equation because it's a Laplace eigenfunction. And so there you have a circle. But I think there's a more fundamental view of where the circle comes from. It's it's likely probably equivalent to this view, but I don't know enough math. But so I think the other view is from the orbit method. In this case, I refer to the orbit method in the spirit of Brumley-Templier. They had a paper in 2014 where they kind of it's like a remark in their paper, but they figure out how to do like the Whittaker function asymptotics for GL2 using the orbit method. And it explains why the circle is there and why there's a whole oscillatory airy decay trichotomy. And so the basic slogan or punchline is that the circle is going to be a k-invariant slice of a coadjoint orbit, and then the Whittaker function, its size is like, okay, well here I wrote that the phase is generated by the projection map to the dual Lie algebra of the unipotent. Okay. Yeah, I should say that maybe some of these remarks are more for any experts, but um, I wanted to put some of these thoughts out there, but I'll try to explain them. Okay. So the basic idea of the orbit method is that you can associate, like, to a representation, you can associate a coadjoint orbit, and then individual vectors in the representation should be associated to regions on that coadjoint orbit. And one of the easiest ones are like, so if you have a weight zero Moss form, which in our case is what we were working with, representationally it's a weight zero form, it generates a principal series representation with parameter t. Its coadjoint orbit is this hyperboloid, and then because the weight zero vector is k-invariant, that's what it means to be weight zero, the right region on the coadjoint orbit is this like k-invariant slice, which is obtained by taking z equals 0. Geometrically, it's like the perp of the Lie algebra of K dual in the dual Lie algebra. But if that's meaningless, then don't worry about it. The point is that I want to say that this is where the circle is coming from, I think. Or at the very least, this circle can explain as much of the behavior that we just saw as like the circle we actually worked with. Okay, so you take a k-invariant slice, and this is called like the microlocal support of your Moss form. And so the point is the Whittaker function actually has an integral representation. Representation theoretically, it's like a functional onto the unipotent. And so on the orbit side, understanding this Whittaker function amounts to understanding the projection of its microlocal support to the dual Lie algebra of the unipotent, which is just a line in this case. So what you really want to do is you want to look at the image of the circle, which is its support, and then you want to study the fibers of this projection map. So unfortunately, I've only just now noticed that this labeling is confusing. These numbers refer to how many fibers are in the projection, but you should think of this as tending off to infinity. And this is like the y value. So here, this line is like where y equals t. When y is t, there's only one fiber in the projection map because these 2 points, as they move over, they sort of coalesce into one. So maybe these 2 points are easier because they're kind of 2 separate critical points. And these are actually the critical points of your stationary phase. And so these will produce oscillatory behavior. But as they move to that right edge of the circle, as y gets close to t, they're going to coalesce into 1 point. And this is going to produce a singularity called an A2 fold. And that singularity produces an airy function. And if you keep going to y past t, then there's no fibers, and so there's no stationary points, which means the integral is highly oscillatory, and then you can do integration by parts to get as much decay as you want, but not exponential decay, but like as much as you want. And so this gives sort of the trichotomy we're looking for, that um, you could kind of understand the Whittaker function by understanding this projection. And then in the last couple minutes, yeah, so this is the point. Stationary phase is going to contribute two contributions, and you kind of get exactly sort of this proposition Anshul and I wrote. And I call it the WKB decomposition because I think this is the same as what would fall out if you did the WKB method from physics. And you could also write it in terms of Airy functions in the transition range as well, but I didn't write that down. And so the orbit method for free produces the circle, and hence this decomposition, and hence you know that they're on the circle already, and so it kind of produces for free what much of our proof is based on. Okay. In the last minute or so, I'm going to go back to this trichotomy. Because maybe you noticed that when I was examining these local factors in the triple product L functions, we had the same sort of trichotomy. It's like oscillatory if the parameters are, smaller. If one parameter is smaller than the other, then it gets a little bit of a boost when they collide, and then it's exponentially decaying when one parameter is too far. And so the same geometry, I would argue that the same geometry that told us about the Whittaker function also tells us about these local factors in the Watson-Ticino formula. And I think this is because there's sort of, in three-dimensional space, there's only really two types of singularities you can have. And triple products turn out to be, from the orbit method point of view, you have like three coadjoint orbits instead of one coadjoint orbit. And then you look at the projection of their moment maps, and so you have you look at the projection of their moment maps, and you sort of count fibers, and sort of the same story holds. And I think for sake of time, and to end on time, I'll not go into that story, but I'll leave the slide up. But yeah, so that's it. Thank you.
Thank you very much for your talk.